Look at this rendering of a silicon microchip. Under severe heat stress, its physical structure begins to warp and crack. In automotive electrical architectures, hardware failure is a thermodynamic certainty. Time, heat, voltage, and vibration ensure that every physical component eventually decays. For decades, the automotive industry relied on FMEA, failure mode and effects analysis. This was a qualitative approach. Engineers looked for potential flaws early in the process and tried to design them out, aiming for a system robust enough to avoid breaking. The ISO26262 standard introduces a different requirement. It assumes hardware will fail and transitions from the qualitative assessments of the past to a quantitative framework called FMEDA, failure modes, effects, and diagnostic analysis. The core premise of FMEDA is control. It requires measuring the system's exact ability to detect a fault the moment it occurs, and then calculating the reliability of the transition to a safe state. To achieve the highest automotive safety rating, ASIL-D, these calculations must be rigorous. During a functional safety audit, assessors reject subjective assumptions. Every claim about a system's resilience must be backed by component-level data. Gathering that data is a brutal process. Reaching ASIL-D compliance requires engineers to navigate three specific systemic bottlenecks. In the industry, these are known as the three hells of FMEDA. Functional safety has evolved into a requirement for calculated resilience. To meet these standards, engineers must now quantify exactly how well a system stands up against the inevitable forces of physical decay. FMEDA uses a bottom-up methodology. Engineers start at the smallest physical unit, resistors, capacitors, power ICs, and assign each one a baseline failures in time, or FIT rate. This measures the probability of a physical breakdown over 1 billion hours of operation. This diagram illustrates a hardware failure path. A fault originates at the base, traveling towards a critical output, the safety goal. A single-point fault bypasses safety mechanisms completely, striking the goal directly. A residual fault hits a defensive barrier, but incomplete coverage allows part of it to slip through. ISO26262 evaluates this using the single-point fault metric, calculating the proportion of failures successfully neutralized by your barriers. Then we have latent faults. These are hidden failures that sit dormant inside the system, causing no immediate harm on their own, but posing a severe risk if a second independent fault occurs. The latent fault metric measures how well your system roots out and protects against these accumulating, invisible risks. Finally, all of these calculations roll up into the PMHF, the probabilistic metric for random hardware failures. This represents the absolute average risk that a critical hardware failure will occur over the entire lifespan of the vehicle. To hit an ASIL-D rating, the math is unforgiving. You must engineer a system where single-point and residual faults account for less than 1% of the total hardware failure rate. Setting up that level of proof requires immense amounts of data. The entire mathematical foundation of these metrics relies on a single input, the base failure rate assigned to every component. If your starting numbers are wrong, the entire FMEDA collapses. This leads us to the first major bottleneck. The functional safety standard does not mandate a single method for calculating base failure rates. The industry relies on an array of conflicting reliability standards, throwing engineers into a dangerous data swamp. We can see the problem in this structural cross-section. The SN29500 standard treats the inner silicon die and outer package as a single undifferentiated block, failing to separate physical interactions. More critically, it entirely ignores the mechanical stress on the bottom solder joints, where the package connects to the board. Because it omits packaging fatigue and solder joint stress, using SN29500 produces dangerously optimistic failure rates. During a rigorous ISO26262 audit, an assessor will tear those calculations apart. Look at this revised cross-section using IEC TR62380. It splits the chip into 3 layers: die, package, and solder joints. It mathematically isolates the variables, calculating failure rates for the die independently from the packaging. Furthermore, it measures how temperature waves expand and contract the board, feeding that stress data directly into the solder joint calculations. Relying on weak standards artificially shrinks your risk on a spreadsheet. In reality, it leaves the physical vehicle with critical structural vulnerabilities completely exposed. Once you have an accurate base failure rate, you have to determine how the component will physically break. We call this the failure mode distribution. Take capacitors. A tantalum chip capacitor and a multi-layer ceramic capacitor are used for similar circuit functions, but their internal physical structures dictate entirely different failure profiles. The rigid ceramic inside an MLCC is highly brittle. Under mechanical stress from the circuit board, microfractures begin spiderwebbing through the internal layers. This distinct physical property drastically skews its failure distribution towards short circuits rather than open circuits. A common engineering error is ignoring these material differences entirely. Engineers working on tight deadlines will blindly assign a generic 50% short, 50% open split to every capacitor, destroying the mathematical integrity of the analysis. To survive an assessment, you have to cross-reference military or aerospace databases, like the MIL HDBK standards. These sources mandate precise failure mode distributions based on actual, observed material properties. The same strict conservatism applies to soft errors, such as transient bit flips and memory blocks caused by ambient radiation. You cannot arbitrarily reduce the baseline failure rate just because you have an error-correcting code in place. The physical event still occurs, and the math must account for it fully. Accurate fit rates cannot simply be copied and pasted from a vendor sheet. They must be aggressively tailored to match the exact physical material and the specific operating environment where the system lives. After determining the baseline failures, we calculate diagnostic coverage. This is the mathematical measurement of how effectively your system's safety mechanisms actually catch those failures in real time. Here we hit the second bottleneck, confirmation bias. Hardware engineers who design custom safety monitoring circuits frequently assume their logic is flawless, plugging 99% coverage rates into their FMEDA sheets. In a lab, a simple pull-up resistor might detect a broken wire perfectly, but in a harsh vehicular environment, electromagnetic interference or unexpected leakage current instantly drops that actual detection coverage well below acceptable safety levels. ISO26262 auditors know this. That is why engineer intuition is meaningless on paper. Diagnostic coverage must be backed up by hard, objective data. The only mathematically acceptable way to prove a safety mechanism's coverage is through a punishing process called fault injection testing. In stimulus-based fault injection, engineers test software limits by deliberately injecting a red flag error packet into the sensor data stream. At the semiconductor level, structural fault injection is used. Engineers permanently jam a core logic gate open, simulating a stuck-at fault, to test absolute hardware resilience. A safety mechanism provides zero mathematical value to an architecture until its capability is physically extracted and validated through thousands of agonizing fault injection tests. Today's software-defined vehicles require the management of thousands of deeply interconnected electronic components. The scale of the architecture is massive. Historically, the industry managed this complexity by relying on massive, macro-heavy Excel spreadsheets to calculate their FMEDA metrics. But hardware development is fluid. A single engineering change notice, like altering the capacity of one resistor, forces an engineer to manually hunt down every connected formula. This creates a cascading nightmare of manual updates that inevitably breaks document traceability. If a hierarchical system is placed on a flat spreadsheet grid, it creates a dangerous flaw, accidentally double-counting failure rates and inflating metrics. The upgrade path is model-based systems engineering. Watch the data shift. Updating the physical properties of a single component in the model automatically ripples through the entire hierarchy. It flawlessly recalculates the overall SEMHF metrics without human error. Adopting an MBSE platform prevents your FMEDA from devolving into a dead compliance document. It transforms the math into a real-time, unbroken map of system risk. Deploying perfect data standards and advanced modeling software will still fail if the engineering departments operating them remain isolated in functional silos. FMEDA is a collaborative exercise. The hardware engineer is the true owner of the physical design. They understand the exact electrical impact of a severed connection, and it is their job to map the correct, tailored failure modes directly into the architectural model. The software engineer must take those hardware mechanisms and optimize the diagnostic code. They bear the responsibility of physically proving the diagnostic coverage through automated fault injection testing, ensuring the math works in the real world. And the functional safety manager acts as the orchestrator. They ensure traceability across the different teams and continuously monitor the live metrics against the final system safety goal. Hardware will degrade. True functional safety is achieved only when the thermodynamic reality of that decay is openly acknowledged, accurately modeled, and mathematically bounded by an integrated, highly disciplined engineering team.